Welcome to the deep dive. Today we're embarking on a journey into a corner of mathematics that, on the surface, might seem incredibly straightforward,
Right?
but it quickly blossoms into surprising complexity and beauty. We're talking geometry, computation, and a particularly fascinating sequence of numbers.
Indeed.
Yeah.
And for those of you who appreciate the elegance of combinatorial counting problems, especially, in number theory, this deep dive is definitely for you.
Yeah.
We're exploring simple triangulations of the plane, specifically focusing on its identifier in the OEIS A000256.
Yeah, this sequence tracks the very specific count of these triangulations, and it reveals some deep mathematical structures.
Okay, so our mission today, let's unpack what triangulations truly are, why they're not just abstract concepts, but actually crucial across diverse fields.
Absolutely.
How we construct them computationally, and then maybe the most intriguing part, especially with the field medal winner here, how mathematicians precisely count their distinct forms.
Well, we try. Get ready for some genuine aha moments,
Yeah,
connecting seemingly disparate ideas.
hopefully.
So let's unpack this concept of a triangulation. When we talk about it in geometric terms, what's the fundamental idea we're grappling with?
Okay. At its heart, a triangulation is simply a way to take a polygon, and this can be a simple shape, or even one with, say, internal holes,
Right.
and subdivide it completely into a collection of non-overlapping triangles.
Okay.
The crucial rules are, 1, these triangles have to meet perfectly, edge to edge.
Edge to edge.
And 2, you can't introduce any new corner points or vertices beyond the original ones that defined your initial polygon.
So it's like breaking down any complex flat shape into its most fundamental indivisible building blocks, triangles. It feels pre-intuitive for 2D.
That's precisely the idea. It's a decomposition. But here's where it gets really interesting, actually.
All right.
While 2D polygons can always be triangulated, you might intuitively think, well, the same must apply to 3D shapes.
Yeah.
Right? Like polyhedra.
Yeah, that seems logical.
But it doesn't. 3D polyhedra, surprisingly, do not always have this property, meaning you can't always break them down into face-to-face tetrahedra without adding new vertices.
That feels like a fundamental challenge to our geometric intuition. Can you give us an example? A 3D shape that just defies this?
Absolutely. A classic example is the Schoenhardt polyhedron.
Okay.
It's a sort of twisted prism, a concave polyhedron. And the thing is, any attempt to subdivide it into tetrahedra using only its existing vertices, well, it inevitably creates tetrahedra that poke outside its own boundaries.
So you can't keep it contained.
Exactly. It simply cannot be broken down internally without adding new vertices, which violates the core definition. It's a beautiful counterexample to what seems like an obvious assumption.
That really highlights the depth here. Okay, back to 2D then. For those simpler polygons, the ones without holes, I remember hearing about ears relating to their triangulations. What's an ear and why is it significant?
Right, ears. So for a simple polygon, every triangulation will have what we call an ear. An ear is essentially a triangle formed by 3 consecutive vertices of the polygon,
Okay.
where 2 of its edges lie on the polygon's boundary, and the third edge is internal, like a diagonal.
Like a little triangle sticking out almost.
Sort of, yeah. The key insight here is that every simple polygon with more than 3 vertices must have at least 2 non-overlapping ears.
At least 2. Okay.
And this property isn't just a curiosity. It's actually the basis for one of the simplest algorithms used to triangulate polygons computationally.
Fascinating how a small geometric detail becomes a foundation for algorithms. Now, beyond being a neat geometric concept, where do these triangulations actually show up? Why should we care?
Well, they're everywhere. Triangulations are fundamental tools in computational geometry and really far beyond. One classic, maybe even slightly whimsical application is the art gallery problem.
The art gallery problem, I've heard of this.
Yeah. Imagine you're designing security for a complicated museum floor plan. The challenge is, place the minimum number of guards or cameras to see every single point in the gallery.
Sounds like a classic puzzle, right? Something you'd see in a logic test. And triangulations help solve it, offering a surprisingly elegant solution.
They absolutely do. The art gallery theorem states that any simple polygon with n sides can be guarded by no more than floor n over 3 guards.
Floor n over 3, so roughly a third of the vertices.
Exactly. And the really elegant part, the kind of aha moment of the proof, hinges on a clever trick involving the triangulation.
Okay.
Once you've triangulated the polygon, you can color the vertices of that triangulation with just 3 colors, say red, green, and blue, such that every single triangle has 1 vertex of each color.
A 3 coloring.
Right. Yes. Then, if you simply place guards at all vertices of the least common color.
The least frequent color.
Precisely. You've guaranteed every single triangle, and thus every part of the polygon is fully covered. It's a testament to how abstract geometry can unlock real-world security solutions with incredible efficiency.
That's amazing, connecting pure geometry to a practical security problem. So from keeping museums safe, where else are these tools invaluable?
Well, they're indispensable in fields like terrain approximation. You have scattered altitude points from a survey.
Yeah.
Triangulate them to create a continuous mesh, a digital landscape that lets us model mountains, valleys.
Digital elevation models, that kind of thing.
Exactly. They're also vital for the finite element method. Engineers use this constantly in simulations.
Right, them.
To analyze stress on a bridge, model fluid flow around an airplane wing, predict heat transfer in an engine. By breaking down complex domains into these manageable triangular or tetrahedral and 3D elements, they can perform highly accurate numerical analyses.
So we're talking everything from designing safer buildings and optimizing cars to predicting weather patterns.
Pretty much. They also apply to areas like motion planning for robots.
Ah, robotics.
Navigating through environments with polygonal obstacles, allowing them to find collision-free paths. And they're used in constructing certain types of constrained minimum spanning trees, where specific pathways or connections absolutely must be included.
Given their broad importance, how do we actually build these things computationally? Are there standard approaches, and what are the trade-offs?
There are indeed many algorithms, each with trade-offs, simplicity versus efficiency. The ear clipping method we touched on for simple polygons.
The one using the ears?
Yeah, that one's often cited as the simplest to understand and implement. It works by iteratively finding and removing those ears until only one triangle is left.
Seems straightforward.
It is, conceptually, but its time complexity is ON2.
O(n) squared. Now, for those less familiar with big O notation, what does that mean in practical terms? Slow?
Good question. ON2 means that if you double the number of vertices in your polygon, the processing time roughly quadruples.
Quadruples. Okay, that scales badly.
It can get quite slow for polygons with many vertices. Think of processing time squaring as n grows. For real-world applications with maybe millions of data points, that's often way too slow.
So I imagine practical applications demand something much faster then.
Absolutely. Faster algorithms exist. For example, certain plane sweep methods can achieve ON log n time.
N log n, better.
Significantly better. It means the processing time scales much more gracefully, closer to linear growth. It's practical for much larger data sets.
Okay.
There's even a theoretical linear time ON algorithm, meaning it scales almost directly with input size, but it's famously complicated.
Ah, the academic special.
Sort of. It's still considered impractical for general use. Finding a truly practical linear time algorithm for polygon triangulation remains an open problem.
Interesting. Now, speaking of building these effectively, not all triangulations are created equal, right? A term that often comes up is Delaney triangulations. What makes them so significant?
Delaney. Yes, they are a truly special class, highly valued for their desirable properties, especially in things like finite element analysis.
Okay, why?
Their defining characteristic is that they maximize the minimum angle among all possible triangulations of a given set of points.
Maximize the smallest angle. That sounds backward. Why make the smallest angle as large as possible? Why is that the goal?
It's absolutely critical for numerical stability and accuracy. Think about skinny triangles, those with very small internal angles.
Right, long and thin ones.
They can cause significant numerical errors in simulations. They're just unstable. By maximizing the minimum angle, Delaney triangulations inherently avoid these problematic skinny triangles.
So you get fatter, more equilateral-like triangles where possible.
Exactly, leading to much more robust and accurate results. A key concept here is the empty circle condition.
Empty circle.
For any triangle in a Delaney triangulation, if you draw the unique circle that passes through its three vertices.
It's circumcircle.
Yes, it's circumcircle. That circle should not contain any other points from your input set in its interior. If it does, that edge is considered illegal.
Illegal? Like a poorly placed support beam creating instability.
That's a great analogy. Yes,
Yeah.
It means the triangulation isn't optimal in that region.
And what happens to an illegal edge? Can you fix it?
You can. If an edge violates this condition, we can flip it.
Flip it.
Essentially, you look at the quadrilateral formed by the two triangles sharing that illegal edge. You swap the illegal diagonal for the other diagonal of that quadrilateral.
Ah, you replace it with the other way to cut the quad.
Precisely. This flipping process doesn't change the vertices, just rearranges edges to ensure the new triangles satisfy the empty circle condition. It creates fatter, more stable triangles and improves the overall angle properties.
And what about polygons with, say, internal constraints, like fixed boundaries, maybe designing around a wall or needing to follow a river exactly?
That leads us to constrained Delaney triangulations, or CDTs.
Okay, constrained Delaney.
These are triangulations, where certain specified edges must be included as part of the final triangulation no matter what, even if they wouldn't naturally satisfy the Delaney empty circle condition.
So you force certain edges in.
You do. They're designed to be as Delaney-like as possible while rigorously respecting these predefined constraints.
Makes sense.
And CDTs can also be constructed efficiently, typically in O log n time, often using techniques like divide and conquer. This makes them highly practical for things like creating terrain meshes that follow riverbeds accurately, or for motion planning where obstacles define mandatory boundaries.
Got it. Okay, now for the part that links this directly to our OEIS series. We're looking at sequence A000256. What exactly does this sequence count? And why are these specific constraints like simple or rooted so important for number theorists trying to count these things?
Right. A000256. It enumerates the number of simple triangulations of the plane with n nodes. Now, the reason for those precise constraints, simple and rooted, is crucial for making the counting problem well-defined in combinatorics.
Okay, break that down. What does simple mean here?
Simple means they contain no separating three cycles,
Separating three cycles.
which is a triangle whose removal would split the rest of the graph into two disconnected pieces. Think of it as preventing a triangle that acts like an internal fence, cutting off a piece of the triangulation.
Ah, okay. No internal fences. And rooted.
Rooted means we fix three specific nodes on the exterior boundary. This basically anchors the triangulation.
Why do that?
Well, these constraints together eliminate ambiguities from, say, just rotating the same triangulation or reflecting it. It ensures that each distinct topological arrangement is counted exactly once.
Ah, so it's about avoiding overcounting due to symmetry.
Exactly. It makes the combinatorial problem tractable and leads to those beautiful, precise integer sequences like A000256.
That really clarifies why mathematicians impose those specific definitions. It's about getting an unambiguous, countable set. Can you give us some of the numbers in the sequence for small? Just the first few?
Certainly. It starts off pretty slow, actually. For any three nodes, there's just one triangulation, a single triangle.
Makes sense.
For n through 4 nodes, still only one triangulation. Imagine a square split by one diagonal.
Okay.
For n of 5 nodes, it jumps to 3 distinct triangulations.
3.
For NT6 nodes, now it's 12 triangulations.
Whoa.
N7 nodes, 52 triangulations.
50.
And E8 nodes, 241 triangulations.
Wow.
And at 9 nodes, 1,173 triangulations.
Over 1,000 already.
Yes. And the sequence continues, growing really quite rapidly. It's amazing how quickly the number of possibilities explodes.
It truly is a single definitive value for each n. This raises the obvious question. For these larger numbers, how on earth do mathematicians figure out these counts? They're not just drawing them all out, surely.
Yes, goodness, no.
Yeah.
Not for large n. That would be impossible.
Right.
These numbers are typically derived using, well, complex combinatorial techniques. Researchers delve into the underlying structure of these triangulations.
I'm looking for patterns.
Exactly. They often find intricate recurrence relations. These define a term in the sequence based on previous terms, allowing for computation.
Like a recursive formula.
Precisely. There are also asymptotic formulas that predict the numbers for very large n, giving you a sense of how fast they grow, even if you can't compute the exact value easily.
So it's a deep area of enumerative combinatorics.
It is. It focuses on developing mathematical methods to count specific types of objects, and it often involves beautiful connections to other areas of math.
As we build these algorithms or count these triangulations, how do computers actually see and store them? What kind of data structures are involved when you're working with potentially millions of triangles?
That's a key practical point. In computational geometry, triangulations are typically represented using two main matrices.
Okay.
First, there's a node matrix. This just stores the geometric coordinates like the x and y positions of each vertex.
So a list of points.
Basically, yes. If you have 100 vertices, your node matrix might be 100 rows by 2 columns for x and y.
Got it. And the second matrix?
The second is an matrix, often called the element or triangle matrix. This defines the topological structure. It lists which vertices form each triangle.
How they're connected.
Exactly. For a 2D triangulation, each row in the element matrix would contain 3 indices, and these indices point back to the rows in the node matrix that make up that specific triangle.
So node tells you where things are, elem tells you how they're connected.
You've got it. But, and this is important, just having those two isn't always enough for efficiency.
Why not?
Well, imagine you need to find all the triangles connected to one specific vertex, maybe a stress point in an engineering model.
Yeah.
Without extra help, you'd have to search through every single row of the element matrix looking for that vertex index. For millions of triangles, that's incredibly slow.
Okay, so you need shortcuts.
Precisely. So we build auxiliary data structures,
Hmm.
things like an edge-to-the matrix, which quickly tells you which one or two triangles share a given edge, or a T2V structure, mapping triangles back to their vertices, or vertices to their neighboring triangles. The real challenge, though, comes in maintaining and efficiently updating all these interconnected structures when the triangulation changes.
Like when you flip an edge.
Exactly.
Ugh.
Or add a new point, or refine the mesh locally. These auxiliary structures act like an intelligent, cross-referenced index. They allow for lightning-fast queries and modifications, which is absolutely critical when you're dealing with millions of elements in real-time simulations or complex counting procedures.
What an incredible journey we've taken today, seriously. From the simple act of subdividing shapes.
Which seems so simple at first.
Right. To the complex algorithms needed to build them, all the way to the fascinating world of counting these structures with sequences like A000256. It really shows how a fundamental concept can just blossom.
It does. It highlights the profound interconnectedness of mathematics, where discrete combinatorics, computational geometry, and applied fields like engineering all rely on understanding these elegant subdivisions of space. It's a great reminder that even seemingly abstract counting problems can have a deep impact on how we model and interact with our world.
So what does this all mean for you listening? Well, next time you look at a map or a 3D model or even just a simple polygon, remember that beneath its surface might lie a hidden integer sequence, like the one we discussed.
Or a clever algorithm.
Or a clever algorithm just waiting to be discovered or better understood. It makes you wonder, what other common geometric structures do you think have hidden numerical patterns waiting to be explored by curious minds like yours?